Okay, awesome. So this is a practice problem. I call it the off-course question. And it's very simply dealing with a pilot who's flying in a certain direction, but the wind is blowing him off course. And I'm actually asking you to determine a distance now, like how far off course is he and what that really means. So here we got a pilot. He begins flying his airplane at 800 kilometers per hour to the west. The wind is blowing at 75 kilometers per hour at 40 degrees south of west. Okay, so I've kind of established my second vector. And then this question is, how far off course? How far off course will the plane be, or you could say, will the pilot be, if the pilot's original destination was 1,700 kilometers west? So I'm given two vectors and their velocities. Okay, so I mean, you could identify them as that's the airplane, and this is the wind. Okay, and this is a displacement. This is a displacement. This was his the distance he was hoping to travel. Okay, so if I'm going to get a distance, it's maybe not obvious how you get that right away, but if you're looking at these two, because you have two vectors, you can find, or at least look at, what the resultant would be and what these vectors should look like if they were added together. So I think pretty simply here, let's draw the airplane first. I'm just going to draw a nice big vector here. I'm going to say that's 800 kilometers per hour to the west. Okay. And where that vector ends, we're going to add the next one because the airplane is experiencing a bit of a crosswind, but also a tailwind. It's kind of a unique scenario, but not like any other. It's pretty typical of what we're going to look at here. So 75 kilometers per hour, 40 degrees south of west. So the wind isn't blowing straight west. It's blowing 40 degrees south of that. So I'll just draw a little vector angle like this. And, roughly proportional. Obviously, 75 kilometers per hour is a lot less than 800. So, I mean, we're just sketching it, of course. It doesn't have to be amazing. This would mean that the airplane in his flight, the pilot is hoping, it looks like the pilot's original destination was 1,700 kilometers west. So that makes sense why he was trying to fly west, okay? He was trying to do this, but the wind is blowing a bit down, so he's not going to fly straight west unless he corrects himself. And so his resultant is going to look something like this. Okay, that's just kind of sketching what is like, well, no, this is sketching what's going to happen if he doesn't change anything. Now, with these parameters, how do we determine off course? So what I mean is, he's going to continue with these vectors if he doesn't change anything over time, over the time that it would take him to reach 1,700 kilometers. So that's like a distance that's way over here somewhere. Okay, let's say if he starts right here, his destination from in between the X's, that's 1,700 kilometers west. He's trying to get here, but he's never going to make it if he doesn't correct anything. And so if we kind of extrapolate his trajectory, if you will, he's going to end up somewhere there, okay? If he's flying straight west and he's just like, okay, I know I'm supposed to fly for so much time, so he just keeps flying, the wind will just keep pushing him off course. And then by the time he thinks he should be at his destination, he'll be like, where's the runway? Where's the airport that I'm supposed to land at? Because he won't be anywhere close. He's going to be a certain distance away. And so this is what I mean by off course. This displacement right here, the difference from where he was supposed to end up to where he actually ends up, that is what I'm calling off course. Okay? That's what I'm going to call off course. So there's other ways you could explain off course, and other students, when I pose these questions, they actually saw different ways to define it, because they're like, well, would he, if he travels the same distance, then maybe he's going to end up here, and then whatever. But I don't want to complicate this question any more than just this. Okay, So what we're saying is when he reaches the, in this case, it's a horizontal displacement. When he reaches that much displacement to the west, how far away from his original target will he be? Okay. So how can we do that? Well, probably the easiest way is to actually find the components of the resultant, okay? Because the two blue arrows are producing a resultant. And so let's do that first and see if that kind of triggers your brain, to recognize how you can use this information. Because I don't, it's not asking me for the resultant, so I don't really need it. But in the course of finding it, you can identify the components, which should make sense here once we look at this. So let's just take care of the airplane first, because that one's nice and easy. His x component should be a negative 800 kilometers per hour, because he's trying to fly straight west. And of course, he doesn't want to have a y component because he's just trying to fly straight west. So that would take care of the airplane. Now the wind definitely has an x and y component. So let's actually find that. The wind's x value would be like this, and the wind's y value would be like that. With a 40-degree angle, I don't have the shortcut, but I'm just going to use it because it's a little faster. If I go cosine of 40 degrees, that gives me the adjacent value, which is going to be in this case, it will be the x value, okay? I just have to make sure that I make it negative because it's to the left. And then sine of 40 degrees times 75. I don't know, you guys are seeing like you have to use sine and cosine every time. So it's just staying sharp as to, did I find the y value or did I find the x value? But you're going to have to do cos and sine and multiply them by the vector. So let's make sure that I did this one right. Okay, so this looks like it's a negative 57.453. I'll tuck that in here. And then sine of 40 times 75. Sorry, I should have more space here. This is going to be negative 2 because it's going down. Negative 48.209. Let's use that. Okay, for my wind. Yay, those numbers look right. Okay, so yeah, now we just add them up. So the resultant will have a total x value of negative 857.453. Okay, actually for the plane, that's nice. He's getting a boost. Okay, he can only go 800 kilometers per hour in his airspeed, but the wind's giving him a nice push. But it's also pushing him south, which he doesn't want. It's pushing him south at this 48.209. Okay? Now the reason I show you this is your clue. This is your helpful information because you actually now have the components for the entire movement of the plane. And I mean, I could redraw it, but you guys can see this. Like the total x value from his origin over is, all of that is 857.453. And then there's just this little bit is the negative 48.209 kilometers per hour. Okay. So let me show you two ways to solve for this displacement off course. Okay. The one is this. You can determine the time. If you know the time that he's in the air, how much time that he's in the air going in the x direction, that will be the same amount of time that he's also going in the y direction. Those two are tied together. Like you can't travel for 4 hours this way, but only go 3 hours to this, like in the vertical, okay? They have to be together. And you'll see that time kind of, it binds these two components together because they happen at the same time, right? For the same amount of time. So in the x direction, what we can say is the total x displacement from where he started to where he was supposed to get, that should have been 1,700 kilometers west. Okay, or you could say negative if you want, but we'll say 1,700. Now, what is the velocity that he is experiencing to the west? Can anybody see that number? I know there's a bunch of numbers up there. Shoal, what do you think it is? There it is. Boom. Okay. In the x direction, he is going 857.453. Okay, I'm just hanging on to that number because I'm not really done. So that means I just got to do that math. And that will tell me how long the plane is in the air. 1.982 hours, just a little under 2 hours. Okay. So I don't know if you guys caught that from before, but if he's flying for this much time in the x direction, how long is he flying in the y direction? How long is he in the air experiencing his y velocity? The same amount of time. Same amount of time. So grab your y velocity. Where is it? It's this guy right here. It means that in the y direction, from here down, and this is the off-course value, from the distance from here to here will equal, that distance in the y direction will equal the y velocity that he's traveling, okay, the velocity that's in that direction, for the same amount of time. Okay, so 48.209 kilometers per hour. In this case, that's to the south, sorry. But we're going to multiply that by 1.982. And did I do that separately? I think I did. Yeah. To three digits, I got 95.6 kilometers per hour to the south. So that's telling me, yeah, if he doesn't change anything, after being in the air for this long, that means he's experiencing this velocity for that much time. Yeah, he's way off course. That's an embarrassing error, though, as a pilot. No pilot will make this mistake, trust me. I mean, if you're flying to like Medicine Hat and then you kind of get where you're supposed to be and you're 95.6 kilometers away from Medicine Hat, like you might be almost at the border, the American border or something. But I mean, hey, I guess if it was a cloudy day, maybe you couldn't see the ground and you weren't watching your instruments. I guess it's possible. So, okay. But if you caught that, in the beginning, I said this is one way to do it. This is one way to answer this question. What I want you to see is there's another way, and it involves using the triangles that you have drawn here, okay? So I already have this triangle, so I won't redraw it, okay? I have my resultant, my total x value, my total y value. This triangle, the velocity triangle, will mirror the displacement triangle. Where's my red? I'll just use black, I guess. No, I'll use blue. My displacement triangle would be from my origin all the way out to my destination. And then this would be my distance off course. And then this would be a displacement resultant, okay? One way else you could look at it this way too. Maybe I could just sketch it a bit smaller. So this would be 857.453, and this would be 48. And this is in kilometers per hour. But to scale, if we scaled it, that would be proportional to a displacement, 1,700 kilometers. The 1,700 kilometers would be proportional to this velocity, and this velocity would be proportional to this displacement right here, that displacement y. So the reason I show you that is this might be even faster. And some of you could, if you look at this, there's actually two ways you could even solve this. One way is you could find this angle, that angle theta right there. How do you think that angle compares to that angle? It's the same. And look, see, even here, if your brain saw it this way, they share the same angle right there. Okay, they have the same angle. So if you use tangent up here, you could find the angle and then put that angle down here, and then you could use tangent, and you could solve for the opposite value, okay? A few extra steps, but it's not impossible. Or if you wanted, you could just see the ratios. This is proportional to this, so then this has to be proportional to that if you really want. So look, 857.453 kilometers per hour. That is proportional to 1,700 kilometers. That has to be the same then as this 48.209 kilometers per hour over some distance. Oh, what did I say was the same in the x direction and the y direction? What did I say was the same? Time. What's this? What's this? Light bulb. Yeah? You're getting time here. This ratio is, we already calculated that, by the way, didn't we? Yeah, it's right here. The ratio is 1.982 hours. That's what this is, okay? But guess what? This has to be the same ratio because it's the same time. So, anyway, whatever. Like you could use tangent. Some students just see the triangle, like I'm just going to use tangent. That helps me. I'm just going to do it that way. Awesome. But if you see this ratio, this is just like cross multiply and divide, okay? 48.219 times 1,700 divided by this. Boom. So, oh, actually, let me do it that way and just make sure that I'm not lying. Okay. 857.453. Okay, 95.579, blah, 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 blah. Round it up, 95.6. Yes. Fist pump, because look at this. Same answer. You can clap if you want, but no, I'm just kidding. No, it's not for me. It's because the math works. You know, like we did it two ways. Your brain like found that your neurons converged on the same axis. Same answer, same neurons firing. Okay? All right. So, I just wanted you to keep that in your notes. It's not using any new math other than I'm pushing you to think now of an extension where you start considering distances now, okay? You do all the math to find the velocities, okay, that's what we're doing with this. But now you're like, oh, well, that means I should be able to determine a displacement now, a distance off course, okay? And you will see questions like that shortly. So, I want to take about 15 minutes here and I want to talk about projectiles. This is the last type of motion that you guys are going to study, and it involves one more level of complexity, just one more. You're like, my brain can't take any more complexity. Yes, it can. You got a lot of storage space up there, so we're going to tackle, oh, you know what, I'm going to move this over here so our local viewers can follow along. Okay. Oh, whoops. Let's turn that just a bit this way. Okay. All right. So just you don't need to write this part. I'm just making a point here because I'm actually going to hand out some notes here in a minute. When was it? I think it was in the 1970s or 80s. There was a group in the United States. It was just researchers. They went to elementary, junior high, and high schools, and they threw this question in front of students to see what they thought the right answer was. It has to do with projectile motion. So what it is, the question looked very similar to this. They had an object that was rolling horizontally towards a cliff, and the object, it rolls off the cliff, and they gave three possible pathways for the projectile, that we're going to call it, or for the ball that was rolling, okay? And maybe I should do this a little more deliberately. But they're saying, which path does it take? So one, it was more abrupt like this. It would go like this and then fall straight down. This one came like a little bit this way and then fell down a bit more like that. And then the last one went like this. okay? And they asked, well, it's kind of relative. We could give it a speed if you want. We'll say it's just going 10 meters a second or whatever, okay? But they asked students which pathway they thought was the correct path. So I'm going to ask you guys, which pathway do you think is the correct path for this projectile? Is it A, B, or C? If an object rolls off a cliff with a horizontal velocity, which pathway is it going to take? A, B, or C? Let's conduct a quick poll. Who thinks it's A? I'm really setting you up, though. Yeah, see, there's no takers. No one picks A? Really? Like, it's falling off a cliff. Okay, who thinks it's B? Ooh, got a few more takers. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9 people thought it was B. Okay, so obviously the rest of you think it's C. Is that a fair assumption? Like, I don't think it's any of those. I think it does this. That's what I think happens. No, it does not do that. It doesn't do that. Okay, so yeah, the rest of you, so what, out of our class today, that's probably, how many are here today? 20, so yeah, there's probably 11 that think it's this. Okay, guess what? This is the correct answer. That's the correct answer. Like, what? So anyway, you guys did way better than average, but I kind of set you up for it. Most people, 60% of people surveyed, and it was mostly students, by the way, not necessarily adults, but even adults would probably maybe not be 100% sure. 60% of people thought it was this, okay? Mostly students. And then what was there? The next one was like 25% thought it was B, and then only 15% thought it was C out of their little survey thing. So they kind of had fun with that because the right answer is C. And I know it doesn't make sense maybe to some of you, but I'm going to try and convince you that that's the case. Anyway, they called it, in their research, they called it the Wile E. Coyote. Wait, how did I spell it right?
Coyote runs off.
Oh, you guys know who that is. I was like, he was popular when I was a kid. So if you guys even know who Wile E. Coyote is, I'm impressed. It means you must have seen some old classic cartoons. But Tim, you were describing it. What does he do?
He runs off the cliff, stands there until he realizes that he's off the cliff.
And then straight down. That's not how it works. Okay. So, but they're like, all these people were heavily influenced by like Saturday morning cartoons or whatever it was. Because that's what they see on the cartoons. Like the guy runs off the cliff and he's like, realizes that he's in and he goes straight down. So, actual projectile motion, what happens is, if there's no air resistance, this horizontal velocity, and I'll show you this in the note, so don't worry about writing this yet because I'm going to give you something. But the horizontal velocity stays the same all the way down. And you're going to hear me say that a lot, okay? So horizontally, if he was going 10 meters per second, then he will keep going horizontally 10 meters per second the whole time he's in the air. So he's maintaining a constant speed horizontally. It's like if I was rolling a bowling ball on the floor at 10 meters per second, and this thing shot off the cliff at 10 meters per second, and I did that at the same time, they would hit each other, okay? They're like, because they're both moving horizontally at 10 meters per second. Vertically, though, what's happening vertically to this object? It's falling down at what rate? So vertically, you are accelerating. And so you'll see this, like initially, he won't have any velocity at all in the y direction, but then he'll start picking up velocity in the y direction like this. And then just before he hits the ground, he's got a huge y velocity. So what we have to do mentally with projectiles is separate the horizontal movement from the vertical movement, okay? Horizontally, you are traveling at a constant speed. Vertically, you are accelerating. So this is the blend of these two vectors, and that's what we're going to get good at in your brain. So the really fun example of discussing this, okay? Let's say that you've got a gun in this hand. Here, let me simulate this. Okay, I got a gun in this hand. I have a bullet in this hand, just like out of the cartridge or with the cartridge, doesn't matter. Like this, okay? If I fire the gun and drop the bullet at the same time. So bang. Which bullet will hit the ground first? Which one will hit the ground first? The bullet that comes out of the gun or the bullet that I drop? Which one will hit the ground first? Okay, you think you got an answer?
They both have gravity working on them, so if they're level,
it will what? Ooh, that's the... Okay, wait, so what you're saying is this bullet's going to come flying out. It's going to have a huge horizontal velocity, but gravity will start acting on it as soon as it comes out of the gun. And so its path will look like this until it hits the ground, okay, like really, really far away. But then this bullet here, it will just fall straight down like this and hit the ground, okay? What you're saying is that this bullet and the fired bullet are going to hit the ground at the same time. Who thinks Tim is right? You guys are like, I know he is, but I just don't want to, draw attention to myself. Yes. No, that's exactly what happens.
right.
So now barring air resistance, right? So, and if there's no air resistance, we're going to kind of say that in most of our questions. Tim is exactly right. Gravity will act on because the bullets are the same mass, okay? Like the one I drop or the one I fire, okay? I guess you shouldn't have the cartridge on it, so it's just the bullet. But anyway, yeah, this bullet will hit the ground. It'll be really, 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 really far away horizontally. In fact, this distance, you'll see we call this range. And that might line up with your idea of if you go to a shooting range, okay, it's the horizontal distance. Oh, and I'm sorry, I have a confession to make, you guys. I know when you're in math and you learn stuff about graphs, someone help me out. The horizontal displacement, that's called the domain, isn't it? And this is called the range. Is that right? Sorry about that. In physics, the range is not vertical. It's horizontal. Okay? So, range. Horizontal, okay? So don't confuse that. I know we're kind of in a different discipline, and I don't know why we got that one backwards. Range is not vertical in projectile motion, okay? Well, yeah, maybe. Okay. So, anyway. Okay. So, the horizontal velocity is staying the same, and but the vertical velocity, I'm sorry, I guess your diagram does that. Sorry. The vertical velocity, initially, you can say that Vy is equal to 0. That's really important to understand for an object that's only moving horizontally off the cliff, okay? The initial vertical velocity would be nothing. But that vertical velocity will change as you go down I forgot to put this on here. As you go down the trajectory. So the trajectory is the path. It's just the path or the pathway of the projectile. Okay? But as you do that, you're going to get a greater and greater y velocity. Okay? And like we said before, if we're considering the final vertical velocity, it is never going to be 0. Okay, like we did before, when objects are in free fall, this final velocity here in the vertical direction won't ever be 0. It'll be the maximum vertical velocity before it smacks into the ground. Okay, so if that's a visual in your head, that's the one I want you to see. And what we should highlight in that is there's two bullets under there. The vertical motion is the motion of free fall or acceleration. The horizontal motion is uniform motion. Where it says the vertical distance is the height, I want to change that. I should have changed that in the notes before I gave it to you. But it should be the maximum height, okay? So not just height, because often the height is just referring to the height of the cliff, which we're going to do that math right away here. But where the vertical velocity is 0, then that will be the maximum height. Sorry, I think I missed where oh, here we go. Because I wanted to put this up here so you guys could see this too. Okay, so yeah, I would make that simple change. Oh, there it is. Okay, here we go. So here it is on your sheet. Right here where it says height, I'm going to change that right now. So that should say maximum height. Whoa, sorry. Okay. And then the horizontal distance is called the range. So again, my apologies on the domain and range confusion here. Range in physics is the horizontal displacement. So in this case, like you can see from the base of the cliff out, so from here out, that would be the range, okay, the horizontal displacement. And we'll look, and so the rest of that just is the bullet versus fired thing. It says, will they hit the ground at the same time? Yes, they will. Both objects have initial vertical velocity of 0, so they'll both fall the same vertical distance down, which means they're going to hit the ground at the same time. So this is the big separation you need to make in your brain. You can kind of highlight these boxes if you want. Vertically, you use all the formulas of free fall. You use all the acceleration formulas, the Furious 5, whatever you want to say. You can put that in here if you want. Vertically, you have to think using the acceleration formulas. Horizontally, that's the easy one. You just use uniform motion. So velocity equals distance over time, distance equals speed times time, whatever, okay? Horizontally, you use the uniform motion. So you can see kind of maybe you can start to sense the progression of what we've been studying. We studied uniform motion, then we studied accelerated motion, then we studied relative motion, which is 2 uniform motions. And now we're studying projectile motion, which is 1 uniform motion and 1 accelerated motion. Okay, so we just upped it in complexity. Okay, so and highlight this at the bottom because this will make a lot of sense when you get into it, and you've already seen it. The only common variable connecting both of these motions is the time. Time is the connecting variable. The amount of time that you are in free fall is the same as the amount of time you're moving horizontally. Time is the same. Okay, so when you'll get to questions where you have to make that connection, and we're actually going to do some of those right now. So let's look at the next page, and I want to just quickly walk through the first 3 questions with you, and just to show you how we apply these 2 formulas. Oh, there's one more thing I'd like you to add underneath these 3 steps. Okay, so anytime you get a projectile motion problem, you can tell it's projectile motion. Numbers 1 is you need to find the vertical and horizontal components of the initial velocity. You have to do that every time, okay? So whatever the initial velocity is, if it's at an angle, which we're going to get to shortly, you need to find x and y. Okay, and then step 2 says use the initial y velocity and the free fall formulas or the acceleration formulas to solve any aspect of the vertical movement. Okay, so you have to find the initial vy, and number 3 says use the initial vx and all the uniform motion formulas to solve everything horizontally. And that's as simple as it gets. Okay, and what you could note under number 3, you could say if no air resistance, which is going to be the case, let's face it. Okay, I'm not going to give you guys an air resistance problem because that's like another level of complexity here. If there's no air resistance, Vx, or the horizontal velocity, stays the same throughout the trajectory. I know I've been using that term. Most of you guys are familiar with that vocabulary word. That just means the pathway of the projectile. So Vx will never change. Once you establish what the initial horizontal velocity is, that projectile will keep that horizontal velocity the whole time it's in the air till it hits the ground, okay? And we don't really deal with it past hitting the ground because that gets into some other math. Okay, so let's do number 1. Do number 1. So we're throwing an object horizontally from the cliff at 20 meters per second. Okay? So if we go horizontally like this, then we already know what Vx is. Okay? It's 20 meters per second. What's the initial y velocity going to be? 0, because I'm throwing it horizontally. We should note that because that'll make sense. You know now, if you're sketching it, which you should do, we should get used to sketching the trajectory. It's just going to do that, okay? It's called a parabolic curve. Maybe I should spell that for you. Parabolic. I don't think that's the first time you guys have ever seen that word, parabolic. It's a parabolic curve. In math, we see that in a number of graphs that we make, okay? But it's because you're accelerating vertically and you continue a constant motion horizontally. It says find the height of the cliff. So we need to find h, or really this, I guess you could say displacement in the y direction. Sorry if you guys can't see that. Or the height. We need to find that. And we need to find the range. Okay? So we need to find how far away from the base of the cliff it will travel. Okay? So here's where we do the separation. Vertically, if I'm dealing with anything vertical, this is a vertical height, I have to use acceleration formulas. So let's find this first, okay? And it gave me one more thing, I didn't say that. It says it took 5 seconds to hit the ground, okay? It said that in the question, sorry, I missed that. So if I'm going to look vertically here, vertically, what do I know? I know that the initial vertical velocity is 0. I know that my time in the air is 5 seconds. What else do I know in the vertical direction? Something I haven't said yet. Hey, there it is. And what is that? Negative 9.81 meters per second squared. That's the number that's burning in your head. So look, I actually know 3 variables, and if I need to find a displacement in the vertical direction, how far it falls vertically, I'm looking for displacement, dy. So we've done this a fair bit already. Can anyone see what formula could work for this if I'm trying to find the vertical displacement? You can look at your formula sheet if you don't remember, but I know some of you have used it enough. You might remember it. Okay, good, Brody, yes. Okay. V1t plus 1/2 at squared. This guy will work all the time. And what's really slick about this, what's going to happen to this V1t right here? What's going to happen to that? Cameron? Yeah, it cancels out because our initial vertical velocity is 0, okay? Remember, this 20 meters per second is not the initial vertical velocity. It's the initial horizontal. So let's just get that guy quick then. It should be 1/2 times the negative 9.81. Meters per second squared times 5 seconds, but that 5 seconds is squared, so it's really 25 seconds squared, okay? Times it by this and cut it in half. This looks like it's a negative 123. That's a really tall cliff. 123 meters. And yeah, you know what? It came out as a negative. That's not wrong though, is it? Why is it a negative value? Because it's what, Amadeo? From our point of measuring, it is below that point by a negative 123, okay? So, I mean, yes, technically, if you were answering this, you'd say the height is equal to just 123 meters. Like you would just say that that's the height of the cliff, okay? But we calculated it to be a negative 123. Okay, good. What about the range? The range is influenced by the horizontal velocity. And what do you guys learn? What did you just learn? What do we know about the horizontal velocity? It's going to stay the same the whole time. And we already know what it is. It's 20 meters per second. So the range is literally the horizontal velocity multiplied by the time. How long is this thing in the air? It's in the air for 5 seconds. So if the horizontal velocity doesn't change, that means horizontally, I'm going 20 meters per second. And I'm doing that for 5 seconds horizontally. while it goes through its movement, right? So yeah, that one kind of came out nice and clean. It should be 100 meters, okay? Horizontally, that turned into 100 meters, okay? Okay, good so far. Now let's throw a little curveball and let's give you an angle this time. So the second one, actually, here, I'm going to give you some space right here. The second one, we throw the ball upwards, I think. Is it up? Yes. We still throw it at 20 meters per second, but we throw it up at 30 degrees now from the top of the cliff, okay? Now, it's not going to stay on a straight line, right? As soon as you let go of it, it'll come to a peak and then it'll make its way down, but it makes a parabolic curve again, okay? So the trajectory is going to look something like this. This question's a little goofy because it still says 5 seconds. So if it reaches the ground in 5 seconds still, then something happened to the height of the cliff, like we're on a different cliff, okay? But they were trying to keep some of the variables the same so you could walk through what we have to do. So we didn't really need to find x and y here because it was only in the x direction. Your first step, like we highlighted right there in the box, you have to find the vertical and the horizontal components of the original trajectory, of the original velocity before you do anything else, okay? So this is where your sine, cosine, tangent just kicks into gear. Okay, let's find both of those. Cosine of 30 degrees times 20. That's going to give me the x value. And yeah, I already did that here. What was that? Yeah, it looks like 17.32. Okay, and it's to the right already, so I'll just leave that. So that's 17.32. Sine of 30 times 20 is, oh, that's right. Sine of 30 is 0.5, so this is 10 meters per second, and that's the y value. Okay, that's how fast it's going in the y direction upwards. Okay. Now, some students, they like to take this and they like to draw that vector right here. That doesn't matter. However you want to visualize that. The initial vertical velocity is 10, and the initial x velocity is 17.32. So if we were to sketch this projectile at different positions on its trajectory, okay, as soon as it leaves the cliff, its vertical velocity will start to decrease. In fact, when it gets to its highest point, the maximum height, the vertical velocity will drop down to 0. But then it'll start to increase coming back down, and it's going to look something like that, okay? Well, I mean, if you want to sketch that, you can. Again, to reinforce this, what's happening to the x component? It stays the same the whole time. Maybe I'll change that to blue. So horizontally, that horizontal component doesn't change. It just locks in, okay, if there's no air resistance. So now what we have to do to find the maximum height, okay? So, actually, wait. Let's not do that one. Let's do the easy one first, okay? The easy one is the horizontal range, okay? Range, again, is the displacement in the x direction. We know the time in the air, and we know that the horizontal velocity doesn't change. So to find the horizontal range, or the horizontal displacement, we just got to multiply those two together because I'm holding 17.32 meters per second. I'm holding that for 5 seconds, okay? So let's just knock that one out of the way first. That should give us whatever, 86.6 meters. Okay, from the base of the cliff out to where it's going to hit the ground. Okay. Again, range is, I'm hoping you'll see, range is like the easier of the two because you don't have to process too many variables. So you just need the horizontal component and the time. Now, to get the height, the maximum height, okay, we actually need to, we already know, actually, wait, no, we don't. We don't know the height of the cliff. Like we don't know how high this is, so I can't find this distance here. Well, I could find this distance here, but I can't add it to anything because I don't know what the height of the cliff is. So what I'm going to push you to see here is we need to find the final velocity v2. Okay, and when I say that, I mean this one right here. If you can find the final vertical velocity right here, it's going to be negative, of course. We already know the initial one is 10. Then what we can find is that'll set us up actually to determine that'll give us the displacement in between the two, though. Yes. Okay. Let's actually do that. So, because I know the time in the air. Okay, so I'll steer you to this. If I want V2 vertically, I'm using an acceleration formula, and I know the time, I know the acceleration, and I know what V1 is. Okay, so very carefully here, V1 is 10. Okay, the initial vertical velocity is 10. The acceleration, of course, is negative 9.81 meters per second squared. And, sorry, I'm running out of space here. The total time in the air, right? This is the hang time. It says the total time that the object's in the air is 5 seconds. Okay, so that's going to mean, so I got to do that anyway, negative 9.81 times 5, and I add 10 to that. I get a negative 39.05 meters per second. Let me make sure I did that right. Yes. Okay, yeah. Okay, plus 10. So this vertical velocity right here is going to be a negative 39.05 meters per second. Okay. So, I can find, oh, yes, okay. I really need the distance from here down, okay? Because I want the maximum height. Oh, wait, no, I don't want that. I don't want that. My brain was getting sidetracked. What do I want? I want the height of the cliff, right? The height of the cliff isn't from here down. The height of the cliff is from here down. From there down. So I want the displacement right here. Okay, sorry, my brain was thinking maximum height, and I was like, I got to do a different calculation. So yeah, I need the displacement from this velocity to this one. Okay, and this formula is going to save the day every time. Okay, I'm kind of speeding up a bit because I know the bell's going to go. You can find the displacement that occurs in between the 10 meter per second velocity and this negative 39.05. Okay, that is going to be my vertical displacement, not up all the way up here. All I care about is from here down. That would be the vertical displacement and essentially the height of the cliff. Okay, so I would rearrange this first. Some of you guys like to put in the numbers first. You could do that if you want, but I like to rearrange it. I got to solve for d, so I subtract vi squared and divide it by 2a. Looks like this. Now substitute in my numbers. Negative 39.05 squared minus 10 squared all over 2 times negative 9.81. And I'm hoping this gives me a negative number when I'm done. Because it should, oh yeah, subtract basically 10 squared, which is 100, yeah. Okay, and then divide that by a negative 9.81, yes. Oh, whoops, I forgot to times that by 2. There we go. Yay. Whew. So I gave me a negative number. Sorry, it's negative 72. Sorry if you can't see that. Negative 72.6 is what I get as a displacement from the point of release to the point that hits the ground. That would be the vertical displacement, which then would correspond to the height of the cliff. So the height of the cliff is 72.6 meters. So yeah, it's like this magical cliff that keeps changing heights. Anyway, the bell's going to go here in just a minute. What I'd like you to try is like number 3 for homework, okay? And then push onto the next page. There's like 1, 2, 3, 4. There's four more practice problems on the other side. We're going to pick up with those tomorrow, and because I want you to walk through them, make sure you can make sense of them. But yeah, try if you can get through like question 1 at least on the next page. And if you're seeing it, like the pattern, you'll be able to pick it up right away. But anyway, so good job today, guys. Listen, you just pack that up here. We got a couple minutes.